Today's topic is static electricity and Coulomb's law. Heads up when you touch a doorknob in winter. Hair standing up after you rub a plastic sheet. Dust pulled onto a television screen. Everyone has met these, and all of them are static electricity. And when you think about it, it is strange. No battery is connected anywhere, yet objects pull on each other or push each other away. What exactly is this invisible force? In this video, we will get to the root of it. The keys are the idea of charge and Coulomb's law. These two are the foundation of everything that follows: the electric field, capacitors, all of electromagnetism. So let us start from the very beginning with what static electricity actually is. So what exactly is static electricity? First, remember the current you learned before. A current is electricity flowing without a break through a wire. To keep it going, you needed something that keeps pushing electricity out, such as a wall outlet or a battery. Static electricity is very different. It is not electricity that keeps flowing, like a current. It is electricity that piles up on an object and stays right where it is. That is exactly what sits on a rubbed plastic sheet or on your body on a dry day. The word static says it. The electricity is not moving. It is sitting still, so we call it static electricity. Picture a current as the electricity that flows, and static electricity as the electricity that gathers and waits. And it is because this electricity is sitting there that the pulling and pushing happen at all. So let us actually watch it happen. Let us watch what the gathered static electricity actually does. Rub a plastic sheet against your hair or a sweater. The sheet will then pull in small scraps of paper and dust. That is a pulling force, an attraction. Now take a second sheet, rub the same way, and bring the two together. This time they slip away from each other. That is a pushing force, a repulsion. Here is what matters. Static electricity is not just a random zap. There is attraction that pulls and repulsion that pushes, and these two forces follow a definite rule. So what is behind this pushing and pulling? To explain it, we need one more idea. We have just seen things pull and push. How can we explain that force? The point is that a rubbed object has taken on something invisible. An ordinary plastic sheet does not pull paper scraps in. A rubbed one does. So rubbing changed something and put the sheet into a state that can create a force. To handle that state properly, we need to express two things. One is how much it has taken on, an amount. The other is which kind it is. The idea we bring in to express that amount and that kind is charge. With charge, the pushing and pulling can be explained cleanly. So let us look at what charge is. Let us define charge. Charge is the amount of electricity an object holds, and it is an amount that carries a sign, either plus or minus. Its symbol is Q, and its unit is the Coulomb, written C. Here is the most important distinction. Charge is the amount of electricity. The current you learned before is the flow of electricity. They sound alike, but they are completely different things. Water makes it easy. The amount of water in a cup is like charge. The flow of water through a pipe is like current. Water does not have to be flowing to exist as an amount in the cup. Charge is the same. Even when nothing is moving, it is there as an amount of electricity sitting on the object. What had gathered on that rubbed plastic sheet was exactly this charge. So how are plus and minus charges created in the first place? The key is the electron inside the atom. An electron is a very light, very mobile particle carrying negative electricity. Normally, an object holds equal amounts of positive and negative electricity, and they cancel out. That state is neutral. As a whole, it carries no charge. But when two objects are rubbed together, only the mobile electrons move across from one to the other. The object that gave electrons away has less negative, so it becomes positive. The object that received them has more negative, so it becomes negative. Watch out for a common mistake here. Becoming positively charged does not mean positive particles flew onto the object. What moves is always the light electron. Positive simply means the electrons have left and are now in short supply. Electricity has only moved and become lopsided. That is what charging really is. Now remember conductors and insulators from earlier. The difference between them explains everyday static electricity nicely. An insulator is something that hardly conducts electricity, such as a plastic sheet, rubber, or dry air. Inside an insulator, charge cannot move from where it is, so the charge you rubbed onto it just stays. That is why static electricity builds up on insulators. A conductor, on the other hand, conducts electricity well. Metals, and in fact our own bodies, are conductors. Inside a conductor, charge can move freely. So when a body carrying static electricity touches a metal doorknob, the stored charge rushes through the conductor all at once. That instant of discharge is the zap you feel. Charge stays in an insulator and moves in a conductor. That difference explains the static electricity you meet every day. Now that we know about charge, let us answer clearly what was behind the pushing and pulling we watched at the start. Bring the two charges close together, and a force acts between them. This force between charges is called the electrostatic force, or the Coulomb force. Its direction follows a clear rule. Like signs, plus with plus or minus with minus repel each other. The force pushes them apart. Unlike signs, plus with minus attract each other. So the two rubbed sheets pushed apart because both of them had taken on the same sign. The dust though works a little differently. The dust itself carries no charge, but when a charged sheet comes close, the electricity inside the dust becomes lopsided, and the side nearest the sheet takes the opposite sign. That is why it gets pulled in. The law that expresses this force, including how strong it is Coulomb's law, which we look at next. Now let us look at Coulomb's law as a formula. The size of the force F between two charges can be written like this. F equals K times Q1 times Q2 divided by R squared. There are only two important points. First, the force is proportional to the product of the two charge magnitudes, Q1 and Q2. The larger either charge is, the stronger the force. Second, the force is inversely proportional to the square of the distance r between them. The denominator is r squared, so distance really bites. The k in front is a proportionality constant, called the Coulomb constant. In vacuum it is about 9 times 10 to the 9th. Here it is enough to remember that such a fixed number exists. One more thing. This formula is about point charges, that is, objects whose size we can ignore, and r is the distance between the charges. Into Q1 and Q2 you put the magnitudes, with the signs removed. The signs tell you the direction, whether it repels or attracts. And this formula does not stop here. It leads straight into the electric field we learn next, the idea of thinking about the force on a charge place by place. The most interesting part of the formula is that it is inversely proportional to the square of the distance. Let us feel that concretely. Keep the two charges exactly as they are and change only the distance between them. Say we move them from 10 centimeters to 20 centimeters twice as far. What happens to the force? When the distance doubles, the denominator becomes 2 times 2, so 4 times as large. The force is the reciprocal of that, so it drops to 1/4. We only doubled the distance, yet the force fell to 1/4. Let us put numbers on it. If the force was 0.04 newtons at 10 centimeters, then at 20 centimeters it becomes 1/4 of that, 0.01 newtons. Move them 3 times as far, and the force falls to 1 over 3 times 3, that is 1/9. So a small increase in distance weakens the force sharply. That is the bite of the inverse square. It is also why static electricity feels weak as soon as you move away. Let us get a feel for how big the unit Coulomb really is. The smallest unit of electricity is the charge on a single electron, called the elementary charge. Its value is about 1.6 times 10 to the minus 19 coulombs. That is an extremely small number. Turn that around, and to gather 1 Coulomb of electricity, you need about 6.2 times 10 to the 18th of these tiny electrons. In other words, 1 Coulomb is in fact an enormous amount. So how much is behind an everyday zap? The charge that moves there is far smaller than 1 Coulomb. Just a slight imbalance of charge produces that whole zap. And one more thing, charge only comes in whole multiples of that single electron's worth. Charge cannot be divided endlessly, and that is worth remembering. Finally, some field knowledge. You may think static electricity is just a slightly annoying zap. In workplaces that handle electronics, it is actually a serious enemy. Even a slight imbalance of charge can amount to several thousand volts. A zap too small for a person to feel can still be that higher voltage. When that high voltage flows into a precision IC or an electronic part, the part can be destroyed in an instant. This rush of stored static electricity is called electrostatic discharge, or ESD. So the field takes it seriously. A wrist strap on your arm drains the charge on your body gently to ground. A conductive mat goes on the bench. Parts travel in special bags that resist charging. All of it is arranged so that charge never builds up. One last aside. The inverse square form of Coulomb's law looks very much like the law of gravitation that acts between the Earth and the stars. But electric force can both attract and repel, while gravity only attracts. They resemble each other without being the same. Let us put today's lesson together with a quick check. 3 questions. Pause the video and think them through. Question 1. Charge means electricity flowing. True or false? Question 2. When a rubbed object becomes positively charged, why? 1. Positive particles stuck onto it. 2. It runs short of electrons. 3. It gained extra electrons. Question 3. Which statement about Coulomb's law is correct? 1. The force is inversely proportional to the distance. 2. The force is inversely proportional to the square of the distance. 3. Charges with the same sign attract. Here are the answers. Question 1 is false. Electricity flowing describes current. Charge is the amount of electricity, not the flow. Question 2 is number 2. An object becomes positive when it runs short of electrons. What moves is the electron, and positive particles do not stick on. Question 3 is number 2. In Coulomb's law, the force is inversely proportional to the square of the distance. Number 1. Plain inverse distance is wrong, and number 3 is wrong because like signs repel. Here is today's summary. Everyday static electricity is an imbalance of charge. Charge is the amount of electricity an object holds carrying a plus or minus sign, with symbol Q and unit Coulomb. It is not the same as current, which is the flow of electricity. An object becomes charged because electrons move. Give them away and you go plus, receive them and you go minus. In an insulator, charge stays where it is, and in a conductor it moves and rushes out once it has a path. The rule for the force between two charges is Coulomb's law. Its size is proportional to the product of the charge magnitudes and inversely proportional to the square of the distance, and its direction is repulsion for like signs and attraction for unlike signs. Keep the inverse square in mind too. Twice the distance gives a quarter of the force. And today's formula does not stop here. In the electric field and potential we learn next, we think about the force on a charge place by place, and Coulomb's law is the starting point. Storing electricity and exerting forces open up from here. Thank you for watching.